Okay, today we're happy to have Pierre-Alexandre Arlove, who will tell us about contact squeezing in various closed frequentizations.
Okay, so Pazit, thank you very much for the introduction, and also thank you very much to the organizers for the invitation. I'm very happy to present this work about contact non-squeezing in various closed frequentization today. And so I will start the talk by talking about what happened in symplectic geometry, and then to what happened in contact geometry, and present my result, and compare what happened in these both worlds, because there are similarities, but there are also differences between contact and symplectic geometry. So first, I think everyone knows that in a symplectic manifold, we don't have any local invariant. So more precisely, there is this Darboux theorem that says that for any symplectic manifold, so a manifold endowed with a closed non-degenerating form, and you will always be able to find around every point P a chart, so that in this chart, your symplectic form looks like the standard symplectic form on R1, which is just omega 0 given by the sum of dxi veg dyi. And for some question of notation, I introduce also this, let's say, standard one form on the R1 that I denote by lambda 0. And actually, the standard symplectic form on R1 is exact. So it's given by the differential of this one form, lambda 0, which is just the sum of yi dxi. And so we don't have any local invariant, but there are, of course, a lot of global invariant. One of them, for example, is the volume. So if you have a symplectic manifold, then your manifold has to be of even dimension. And if you take the symplectic form to the power n, it gives you a volume form. And if you take any symplectomorphism, so a diffeomorphism that preserves the symplectic structure, it will have also to preserve this volume form. So volume is preserved by symplectomorphism. And for a long time, it was an open question: is the volume the only, let's say, global invariant of symplectic geometry, or can we find some kind of finer invariant? And this was formalized by the Gromov alternative. And then Gromov himself proved in 1985 is a very beautiful and famous theorem about non-squeezing, which says that there exists a symplectic embedding of a ball of radius little r inside a cylinder of radius big R, if and only if little r is less than big R. And then, of course, if you were asking only for volume preserving diffeomorphism, you would be able to squeeze the ball into the cylinder, since the cylinder is infinite volume. So now let's go to what happens in contact geometry. So first, definition: contact manifold is a manifold endowed with a distribution of hyperplane, which is co-orientable, which means that there exists a vector field everywhere transverse to this distribution. And moreover, we ask the distribution to be maximally non-integrable. And one way of seeing it is, another way of saying the same thing is to say that the contact distribution is given by the kernel of one form alpha, so that the exterior derivative of alpha restricted to the distribution is non-degenerate. So in some sense, the alpha is a symplectic form on the distribution of hyperplane. And actually, there are links between contact and symplectic manifold. One of them is to go from contact manifold and to get from it a symplectic manifold by the process of symplectization, which is not the process we will work with today. It's more the other one. So the symplectization, just you take a contact manifold and then you take the product with R and you get a symplectic manifold by this taking this symplectic form. Okay. The thing we will be more interested today is the other. It's to go in the other direction. So you start with a symplectic manifold and then you associate to it a contact manifold. And one way to do so is when you start with an exact symplectic manifold. So a symplectic manifold such that omega is given by the differential of a one form. Then if you take the product with R of the symplectic manifold, you can look at the kernel, the distribution given by the kernel of the one form dz plus lambda. And this will give you a contact distribution. And actually, since the one form dz plus lambda is invariant by a translation in the R direction, then you can quotient this one form descends to a one form on W times S1. And this is more precisely what we call the prequantization. It's more the W times S1. Okay. And later on, we will talk about more general prequantization, but this is a first example of prequantization that are open, actually, because if you have a symplectic manifold, which is exact, it has to be open. Okay. So again, in this contact geometry, we don't have any local invariant. So if you have a contact manifold, around any point of your contact manifold, you can find a chart so that the contact distribution is just given by the kernel of the one form dz minus the sum of yi dxi, which is the standard contact distribution on R2n plus 1. Okay. And moreover, in this geometry, we have even more flexibility than in a symplectic geometry. And actually, we cannot expect non-squeezing phenomena as in symplectic geometry, since in the standard contact manifold R2n plus 1 with this with its standard contact distribution, the map x, y, z maps to ax, ay, a square z is a contactomorphism. So for example, if you take a very big ball, you can send it in a neighborhood as small as you want of 0 if you take A to be small enough. Okay. So when you combine the theorem with the lemma, we don't have any hope of Gromov type non-squeezing theorem. Okay, because locally your manifold look an open set of R2n plus 1, and in R2n plus 1 you can squeeze everything. So you can squeeze a ball of radius as big as you want inside your contact manifold. So if we want to talk about non-squeezing here, we will have to be a bit more precise and more restrictive at least. And the difference here will be that we will work in an ambient contact manifold. Okay, so the ambient contact manifold here in the definition. So okay, more precisely here, what I define is contact squeezing, not contact non-squeezing. So you take an ambient contact manifold M, and then you say that a bounded set U inside M can be contactly squeezed inside in set V inside your contact manifold M psi if there exists a contact embedding of U in V, but you ask also that this contact embedding can be extended to a contactomorphism phi, which is a contactomorphism over the whole contact manifold, and moreover, which is isotopic to the identity. And for example, in this picture that I've drawn, so it might be possible to squeeze this solid torus, the orange solid torus, so not squeeze, to, let's say, embed the orange solid torus inside the thin blue solid torus. But then if you look at these tori inside the bigger black solid torus, then maybe you cannot squeeze the orange one in the blue one by staying inside this black torus. And actually, this is what happened. And it was shown, maybe if you have a question here. Okay. And actually, this is what happened. And so the first embedding is possible, while the second is not. And it was proved by, it was proved by Eliashberg, Kim, and Polterovich in 2006. So more precisely, if you work in R2n times S1, so here by convention, S1, I see it as of length 2 pi, okay? And with the standard contact form, so the one from R2n plus 1 that descends to R2n times S1. So the theorem of Eliashberg, Kim, Polterovich says that if you can, the ball of radius big R times S1 cannot be contactly squeezed in the cylinder of radius little r times S1 inside the contact manifold R2n times S1 if there exists a multiple of 2 pi that separates pi little r square and pi big R square. And actually this, there is this multiple of 2 pi that separates pi little r square and pi big R square is important here because they show also, Eliashberg, Kim, and Polterovich, that if the pi R square are less than 2 pi, then you can contactly squeeze the ball inside the cylinder when n is large enough. And actually, this 2 pi, we will see, we will have similar results, and this 2 pi corresponds to the period of the red flow. I didn't mention the red flow yet, but we will see it very soon. And yeah, this is a geometric way of thinking about this 2 pi. And yeah, another remark is that there were similar results obtained by Peter Albers and Will Mary, not in R2n times S1, but in W times S1, so in the prequantization of Liouville manifolds. So Liouville manifolds are special kinds of exact symplectic manifold. And as I said before, they have to be open. And today, the result I want to present is something similar, but for closed prequantization. So if no question, maybe I move to definition of prequantization. So first, a red flow. So if you have a contact manifold, you fix a contact form, then to any contact form, you can associate a vector field, which is called the Reb vector field, which is uniquely determined by these two equations. So the contraction of this vector field with d alpha is always 0, and the contraction of this vector field with alpha is equal to 1. So, and the flow of this, so we will admit today that this vector field is complete. Actually, we will work with a closed manifold, so it will be complete. And the flow of such a vector field are called the red flow. Okay. And then S1 principal bundle of a contact manifold over a symplectic manifold is a prequantization if there exists a contact form supporting the contact distribution such that the pullback of the symplectic form is exactly the exterior derivative of this contact form, and that the Reb flow of the contact form induces the free S1 action. So every orbit of the Reb flow is of minimal period 2 pi, okay? The same minimal period. So some remark before moving to example and the statement of the theorem. So if you have a prequantization, then you have actually a sequence, the sequence of contact manifold. So just for any integer k, you can see zk, so the cyclic group of order k, as a subgroup of S1, seeing them as a k roof of unity. So since S1 acts on the contact manifold M1, zk also acts on this contact manifold M1. And then you get a new contact manifold, which I denote by mk, which is M1 quotiented by this action of zk. And yes, the contact distribution descends well to mk, And I denote by alpha k the only one form on mk, such that its pullback is equal to the first one form alpha 1. So let's say alpha 1 was Zoll of minimal period 2 pi, and alpha k will be Zoll also, so every orbit will be periodic, but now the minimal period will be 2 pi over k. So it's not exactly a prequantization. If you want it to be a prequantization over W, you have to multiply this form by k, and yeah. Okay, so this just a bit technical, but yeah. What is important to remember is that the rep flow of alpha k is of minimal period 2 pi over k. And that I denote pi k the projection of mk onto W. Okay. So if you have no question, I move to the first example of prequantization. That will be also important for our theorem, because it will be, the theorem will hold for this kind of prequantization. So if you start with the sphere, the standard contact sphere in R1 plus 2. So what is the standard contact sphere? It's the sphere endowed with the distribution given by the kernel of the, let's say, radial one form on R1 plus 2, which is given by this formula. And if you look at the red flow of this radial one form, it is just the multiplication by exponential it. Okay, so in particular, the red flow is 2 pi Zoll, so it's periodic of minimal period 2 pi, and so you get an S1 action on the sphere. And when you quotient the sphere by this S1 action, you get what is called usually the complex projective space, so CPN. And then if you look at the K roof of unity, what you get is exactly what we call usually length spaces. So when K is equal to 2, usually we call it the real projective space. And when K is greater than 2 is length spaces. And this is a general lemma. So if you start with a contact manifold whose rep flow is periodic of period 2 pi with all orbit of the same minimal period, then you can associate with a prequantization by quotienting your manifold by this action of the rep flow, you get a prequantization. Okay. Okay. So now this is the main theorem. So you start with a prequantization, which is either the sphere over the complex projective space that I have just described, or you suppose that M1, so the first prequantization, is strongly orderable. So I didn't say yet what is strongly orderable. I will give some examples just after the theorem, and will give the definition during the proof. But to have some maybe examples in mind, since now, you can think about a manifold, a contact manifold which is hypertype, for example, so that admits one form, a contact one form whose rep flow does not have any contractible rep orbit, or that admits a symplectic, a Liouville filling, such that the symplectic homology of this filling does not vanish. Okay. So the theorem is the following. So you start with a symplectic embedding of a ball of radius big R inside your symplectic manifold. And then for any real numbers A1 and A2, where A2 is small with respect to big R, if you can find a multiple of 2 pi over k that separates pi A2 square and pi A1 square, then you cannot contactly squeeze the contact ball of radius A1 in the contact ball of radius A2 inside your contact manifold mk psi k. Okay. And here what I call the contact ball of radius A, you just take the symplectic embedding of the ball of radius A into W, and then you lift it to your contact manifold mk by the projection. Okay, so some remark about this theorem. So first, it is not empty in the sense that if I start with any symplectic embedding for k big enough, so a symplectic embedding of a ball of radius big R, let's say, then for k big enough, 2 pi over k will be very small with respect to R. So I will be able to find A2 and A1 such that pi A2 square and pi A1 square are and are separated by a multiple of 2 pi over k. And so I will be able to detect some non-squeezing. Okay. And of course, if we don't ask about this squeezing to be contact, then you can squeeze everything. If you just ask for smooth squeezing isotopic to the identity, you can always smoothly squeeze the ball of radius A1 inside the contact ball of radius A2. Another remark maybe that is interesting is that if you take, actually there is a result of Karlsson and Tolman that says that you can embed, let's say, sufficiently big ball into CPN, so the complex projective space, such that with our theorem, you can even detect non-squeezing when k is equal to 2. Let's say if you start with your prequantization, which is the sphere over the complex projective space, with the embedding of Karlsson and Tolman, we will be able to detect non-squeezing even in the real projective space. So we don't need to go k very big. We can do it even for k equal to 2. Okay. So maybe some remark about the hypothesis about, before stating some examples of strongly orderable contact manifold. So the fact that A2 has to be small with respect to R, maybe this 1 over square root over 3 can be, it can be a bit better than that, but for the moment I cannot. And it's just that I need enough room to displace the ball, the contact ball A2 inside the contact ball of radius big R. So this is why I need A2 to be not too big with respect to big R. And then there are 2 hypotheses also about k has to be greater than 2. And actually, j is strictly smaller than k. So the multiple of 2 pi over k that separates pi A2 square and pi A1 square actually is less than 2 pi. Okay, so this is also a bit technical assumption. But maybe we will see during the proof. Maybe it's easy to see during the proof why we will need this assumption. Okay, or maybe you have a question. Okay, if no question,
I have.
Sorry.
Since it's a bit hard to read, can you briefly compare your result with the previous ones? So there is intersection, part is new, part covers, or how is it?
But actually, the previous one was when the prequantization was prequantization of a Liouville manifold, so W times S1. And here it's for closed contact manifold. Okay.
Okay.
So to have in mind more, it's let's say the sphere of a complex projective space. So it's in this sense, it's different. I think it's
everything
more.
new. Everything new.
Everything new. Yeah. I think so. Yeah. I think there was a result of Igor Uljarevich. I'm not sure how to pronounce well his name. Where he was able to find some non-squeezing also in closed contact manifold. But for the contact manifold he was considering was the sphere, but not with the standard contact distribution, with some exotic contact distribution. And except from that, I think for closed contact manifold, maybe in a unitary cotangent of the torus also you can use some tools to find non-squeezing using the shape invariant. Actually, that was presented last week by Richard Hint. But except from that, in closed symplectic manifold, I think that there are no much about non-squeezing. So I reply to your question, Felix.
Absolutely, yes, thank you.
Yeah. Okay. And okay, so some example, yes, of strongly orderable prequantization. So closed strongly orderable prequantization. So you start with a closed Riemannian manifold whose geodesic flow is 2π. So the geodesic flow is periodic with same minimal period. Then you take the unit cotangent bundle, and this is strongly orderable by a result of Collin-Chantraine Dimitroglu-Ritzel because it admits a Liouville filling whose symplectic homology does not vanish. And the red flow actually is almost the geodesic flow, so it's also 2π. So it's an example of strongly orderable prequantization where we can apply our result. Another way to construct a strongly orderable prequantization is that if you start with a symplectic manifold such that the symplectic form is integral, so because of our convention is not integral, but it takes values in 2πz, oops, then you can associate to any S1 principal bundle over W whose Euler class projects to omega over 2π. This S1 principal bundle will admit contact form whose red flow induces the S1 action and such that the pullback of omega is exactly the alpha. Okay, so you can associate to it prequantization. And if you ask, sorry, oh, yeah. Okay. I don't know, there is a problem in this. If you ask the symplectic form more to be aspherical, then your contact manifold will be strongly orderable because actually it will be hypertight. So the red flow will not admit any contractible Reb orbit. And then you can use a result of Collin-Chantraine Dimitroglu-Ritzel to deduce that it is strongly orderable. Okay, so this is another example where our theorem applies. So how we will prove this? So if do you have a question? If not, I'll move to the idea of the proof. So to prove this theorem, I construct a contact capacity. So just a notation. So I will say for any positive real number t, I will call the t integer part of a number x the smallest multiple of t greater or equal to x. And then for what I show is that for any integer k, there exists a map taking open sets of the contact manifold mk, taking value in R, positive real numbers, maybe plus infinity, such that it is monotone. So if U is a subset of V, the capacity of U will be less than the capacity of V. The 2π over k integer part of the capacity of U is invariant by contactomorphism isotopic to the identity. And then we have I compute also some estimates. So the capacity of the ball of radius little r will be a contact ball of radius little r will be less than pi r square. And the capacity of the ball of radius little r will be bigger than the minimum of 2π or pi r square. Where again, the contact ball, what I mean by the contact ball, I start with a symplectic embedding of a ball of radius r inside W, and then I lift it to, I take the pre-image of this ball by the projection. This is what I call the contact ball. So topologically, again, it's a B2n times S1, okay? And once we have theorem B, actually, theorem A is an easy consequence of theorem B. So I just say in 2 lines, maybe how we deduce theorem A from theorem B. So if you suppose that you can send a big ball inside a small ball by a contactomorphism isotopic to the identity, then using the first property, so the monotonicity property, the capacity of the image of this big ball will be less than the capacity of the small ball. But then using the second property, actually the capacity, the 2 pi over k integer part of the capacity of the image of the big ball has to be equal to the 2 pi over k integer part of the capacity of this big ball. And then you use the estimates 3 and 4 to deduce the contradiction. Okay. So this is how it goes. So now the question is how we construct this contact capacity. So first, the idea is to associate to a domain. So the contact size of the domain will be the biggest size of a contact isotopy that is supported in this domain. So I didn't say yet what is the contact size of an isotopy, but this will be the idea. We will associate a size to a contact isotopy. Okay, and actually the number we will associate to a contact isotopy will depend only on the homotopy class of this isotopy. Okay, so the map C actually descends to what I denote by the cont tilde of MXI, which is the universal cover of the group of contactomorphism isotopic to the identity. So a concrete way to see this universal cover is exactly you take the space of contact isotopy starting at the identity, and you identify two isotopies if they are homotopic relatively to endpoints. So this is the concrete way we will use to work with the universal cover. Another way, a bit more abstract, you can put a topology on the group of contactomorphism, and then you look at the universal cover of this topological space. It gives you the same, but this is a bit more abstract, and this is not the viewpoint we will adopt today. Okay. So how to associate numbers to contact isotopy? First, we will associate a set of numbers to contact isotopy, and then the map we will construct will select one of the elements of the spectrum. Okay, the set of numbers is called the spectrum, and the map will select one of the elements of the spectrum. So you take phi tilde, an element, an element in cont tilde, and you say that X is a discriminant point of phi tilde if the time one of your contact isotopy fix X, and that the time one of your contact isotopy preserve the contact form at X, and not only the contact distribution. Okay, and actually this definition does not depend on the choice of a contact form, even if it seems to depend, but it does not, and it was introduced by Giventhal. And the second definition was introduced by Sheila Sandon. It's about translated point, and this definition does depend on the choice of a contact form. So you say that X is an alpha translated point of phi tilde with translation T, if X is a discriminant point of phi alpha minus T, so the rep flow at time minus T composed with phi 1. And then the spectrum of phi tilde is just the set of all translations of translated points of phi 1. So a little lemma. So as I said, the notion of discriminant point does not depend on the contact form, but only on the contact distribution. So we expect some naturality, and actually there is. So if X is a discriminant point of phi tilde, if and only if psi of X is a discriminant point of the conjugate of phi by psi. And also I've received a lot the question why we call this set spectrum. And maybe one of the reasons, it's not me that I've denoted it by the spectrum for the first time, but I think this set is not always discrete, even if it is very often discrete, but it's not always discrete, but at least it's always nowhere dense. Okay, so maybe it's one reason why it's called a spectrum. Okay. And another more maybe geometric way to see this spectrum is you start with a contact manifold, then you can always associate to it a bigger contact manifold, which is m times r, given by the kernel of the distribution, whose contact distribution is given by the kernel of the one form alpha 2 minus exponential theta alpha 1, where alpha 2 is the projection, the pullback of alpha, the projection on the second factor, and alpha 1 on the first factor. And actually, the rep flow of beta is almost the rep flow of alpha. Okay, it's given by this formula. And then to any contactomorphism, you can associate with a submanifold of m times r. And actually, this submanifold is what we call a Legendrian. So it's everywhere tangent to the contact distribution. And then t translated point of phi tilde will correspond to rep code of length t between the graph of phi, the time one of this isotopy, and the graph of the identity. So I don't know how much the picture is accurate here, but the graph of the identity is what I drawn in blue, so it's the diagonal. The graph of phi is the pink curve, and then the rep codes is what I put in green. Yeah, it's not very accurate, I guess, my picture, but just to have something more geometric in mind. And so the theorem is the theorem C that will imply theorem B is the following. So actually the theorem A, which was this non-squeezing, was actually a theorem in some sense in two parts. One part was for the sphere over the complex projective space. So it was one family of prequantization. And then there was another family of prequantization, which was this strongly orderable prequantization. And why I say it's in two parts, because actually the techniques, the tools used to prove this theorem are use two different techniques. So for the sphere, we will use Giventel's nonlinear Maslov index, and for strongly orderable prequantization, another kind of technique. So so this is why also this theorem C is the first part for the sphere over the complex projective space is with Simon Allais, Sheila Sendon, and the second part for strongly orderable quantization, I did it alone. So if the prequantization is either the sphere or is strongly orderable, then there exists a map from cont tilde of mk to r, which is spectral. So it takes a contact isotopy and associate to it an element of its spectrum, such that, and actually I will list a list of properties here, axiomatic properties that this map satisfy. And with these properties, so some of them are a bit technical, but I put all of them here just to say that with all of them, and only all of them, you can prove theorem B, okay? So the first one is that we have a triangle inequality satisfied by these selectors. So if you take a contact isotopy that can be represented by a isotopy of strict contactomorphism, so contactomorphism that preserve not only the contact distribution, but also the contact form, then you have a real triangle inequality. So C of psi tilde phi tilde is less than C of psi plus C of phi. If you ask your contact isotopy to be just a normal isotopy of contactomorphism, so preserving just the contact distribution, then you still have a triangle inequality, but with a 2 pi over k integer part. Then it's compatible with the order. So I didn't say what is the order, but one way of thinking about the order is you say that phi tilde is less than psi tilde if you can find an isotopy connecting phi tilde to psi tilde, such that if you take the speed of this isotopy and you contract the speed of this isotopy with alpha, you get something non-negative. Or in other words, you can find a Hamiltonian function for phi tilde, which is less than a Hamiltonian function that generates psi tilde. And so if you have phi tilde less than psi tilde, then C of phi will be less than C of psi. So something a bit trivial here. So C of the identity is equal to 0. And some non-degeneracy property. So if phi is greater than the identity and phi is not equal to the identity, then C of phi is strictly positive. And finally, something a bit technical, but maybe I just say roughly speaking. So if you start with a contact isotopy in MK, then you can lift it to a contact isotopy in the first prequantization M1. And actually, we are able to make links between C of the let's say, spectral selector of the contact isotopy downstairs with the lift of this contact isotopy. Okay, so this is, in some sense, what these 6 technical points say. Okay, there is a link between the contact isotopy downstairs and the lift of this contact isotopy. So yeah, very quickly, how we construct this map with Sheila Sandon and Simon Allais for when the prequantization we consider is the sphere over the complex projective space. So we do it by using Givental's nonlinear mass Love index. So roughly speaking, what the Givental nonlinear mass Love index does, so you take the space of all contactomorphism, and then inside this very big space, you can look at a subspace, which is the set of contactomorphism that has a discriminant point. Okay, so the set of contactomorphism that admit a point x such that phi of x is equal to x, and at this point, this contactomorphism preserves the contact distribution, the contact form also. So this subspace is, in some sense, hypersurface, orientable hypersurface inside the space of all contactomorphism. And then if you take a contact isotopy, the Givental's nonlinear mass Love index counts with multiplicity how many times you have crossed this hypersurface. Okay, and it uses actually generating function techniques to be defined. So, so yeah. So one of the property of the Givental's nonlinear mass Love index, actually, it has a lot of property. For example, some continuity property and quasimorphism property. But one of them is that, maybe the most important, in some sense, is that if you take an isotopy such that at the time S1, the nonlinear mass Love index is different than at the time S2, then it means that there exists a time U in between such that your contact isotopy at this time has a discriminant point. And then the definition of our spectral selectors. So yes, I didn't say the first one to define the nonlinear mass Love index was Givental, actually, on the real projective space. And then this was generalized by Grandjacques, Carchon, Pabignac, and Sandon for length spaces. And then how we define our selectors, we take the smallest t such that the nonlinear mass Love index of phi alpha minus t phi is less than 0. And then we have to show that this map satisfies all these 6 properties of theorem C. So we have to be more careful about the properties of the nonlinear mass Love index, of course, but at least maybe you can have a rough idea of why this map will select a value of the spectrum, because this number change exactly when you have a discriminant point. And this map having a discriminant point is exactly the same than saying that phi has a translated point of translation t. Okay, so yes, then this is a bit technical, but yeah, the Givental nonlinear mass Love index is constructed using generating function techniques. And then, so this was for first part, so how we construct the selectors for the sphere of a complex projective space. Then for strongly orderable prequantization, the construction goes as follows. So you start, as before, with a contact manifold M. And then you take this big contact manifold M times R with the contact distribution given by the kernel of this form we already seen before. Then, as I said, to a contactomorphism, you can associate a submanifold, which is a Legendrian, which means that, it's a submanifold that is everywhere tangent to the contact distribution. And moreover, it's of a maximal dimension. And actually, when you have, so if you have an isotopy of contactomorphism, then you have an isotopy of Lagrangians, so a path of, not Lagrangians, sorry, Legendrians. So you have a path of Legendrians. And when you have a path of Legendrian, you can associate to it what we call its Hamiltonian function. Okay, so you take any parametrization of this path, you take the speed of this parametrization, contraction with beta, it gives you a function, actually, that does not depend on the choice of parametrization. Okay, and this is called the Hamiltonian function. And then to this Hamiltonian function, you can, so then to this path of Legendrian, we can associate a number. Here I call it the positive length. I'm not sure it makes complete sense, but yeah. So the positive length of this isotopy is the maximum of the Hamiltonian function. Then the number I associate to isotopy phi tilde is the smallest length of all isotopies that are, so Legendrian isotopies that are homotopic to the Legendrian isotopy given by the graph. Okay. So this number, of course, can be minus infinity. And the theorem is that if MC is orderable, so strongly orderable, sorry, and what it means to be strongly orderable, so finally, definition of strongly orderable. So it means that you don't have any contractible loop of Legendrian based at the graph of the identity, such that the length, such that this loop is negative, okay? What it means that the loop is negative, it's that its length is strictly negative, okay? So if you don't have such kind of contractible loop, then actually this number is finite and it satisfies all the properties of theorem C, okay? So this was the construction of these two selectors. And now, yeah, maybe I move on if you don't have any question. Okay. Okay, sorry. So now the aim is to prove how theorem C implies theorem B. Okay, so just a reminder. So how we build our contact capacity again. So we have our selectors, then the capacity of a domain U is the supremum of the spectral selectors of a contact isotopy supported in U, okay? And the theorem B again is that by doing so, we claim that the capacity is monotone. Actually, with this definition, it's trivial that the capacity is monotone. So this is just by definition. So if U is a subset of V, then C of U will be, the capacity of U will be less than the capacity of V. Then we have the 2 pi over k integer part is invariant by contactomorphism. And then we have these two estimates. So the first point, as I said, is trivial. In the remaining time, I try to show how it works to prove the 3 over properties. Okay. So the first one really follows from the periodicity of the red flow. And more precisely, it will follow from the fact that the spectral selectors are conjugation. The 2 pi over k integer part of the selectors are 2 pi over are invariant and conjugation. And this will this implies directly that the capacity is invariant by contactomorphism. So, and why I say that this really use the periodicity of the red flow, it's because, yeah, when actually the periodicity of the red flow allows to make a very strong link between having discriminant point and the spectrum, which is not the case usually. So usually I don't even know if you can read from the spectrum if a contactomorphism has a discriminant point or not. But when the rep flow is periodic, there is a, let's say, a dictionary between having discriminant point and the spectrum. So in particular, if phi tilde does not have any discriminant point, so I want to prove the lemma that the spectral selector are the 2 pi over k integer part are conjugation invariant. So first, I assume that phi tilde has no discriminant point. Then this is if and only if it does not have any multiple of 2 pi over k inside its spectrum. Okay. So now you take any psi t that join the identity to psi tilde of the lemma. Since discriminant points are invariant in the conjugation, then the conjugate of phi tilde by psi tilde does not have any discriminant point neither. And so the spectrum will not contain any element of a multiple of 2 pi over k. Okay. And then if you assume by contradiction that there was a multiple of 2 pi over k that separates C of phi and the conjugate of phi by psi tilde, so at some time t by continuity, C of psi t, phi tilde, psi t. The conjugate of phi tilde by psi t would have to be equal to a multiple of 2 pi over k, which is a contradiction. Okay, so this is how it goes, and this was let's say an argument already used by Sheila-Sandon a long time ago. Okay, and so yeah, here we have made the assumption that phi did not have discriminant point, and you can. But as I said, having a discriminant point is like it's a hypersurface in the set of contactomorphism. So by density, you can always approximate something that has discriminant point by a sequence of things that does not have discriminant point, and you get the result. Then why actually a question that the first question I asked when I tried to define this capacity is why this capacity is finite. And this comes from the same reason, a bit the same reason of about what happens in symplectic geometry, about energy capacity inequality. So what it means that if contactomorphism displaces a domain, then the capacity of this domain will be less than the energy of this contactomorphism. So more precisely here, when I say that a contactomorphism displaces a domain, I say alpha displaces a domain if the time one displaces not only the domain, but the whole orbit of the domain, the orbit under the rep flow. Okay. And then, as I said, so if you take a contactomorphism that alpha displaces a domain U, then the capacity of U is less than what I call here the energy of psi, which is the sum of these two things. And if moreover you assume psi to be a strict contactomorphism, then you say that the capacity of U is you can forget about the 2 pi over k integer part. And the proof is looks similar also as what happened in symplectic geometry. So you start, so you want to show that the capacity is less than the energy. So you start with any element which is supported in U. And actually, since it is supported in U and psi tilde displaces U, then psi tilde displaces the support of phi tilde. And from this, you deduce that the spectrum of psi composed with phi is just equal to the spectrum of psi. Sorry, I received something in the chat, I don't know. How do you know the right-hand side of the inequality? The right-hand side? The spectral selectors we have defined are always finite. So the spectral selectors is a map that goes from the contactomorphism or contact isotopy and associate to the contact isotopy a real number. And this is always finite. Okay. So so it associates to a contactomorphism an element of its spectrum. So I don't know if I answered the question, but it's a bit like the let's say the spectral invariance in symplectic geometry. Okay, so the spectral invariance take a Hamiltonian symplectomorphism and associate to it a real number which is finite. And for the same reason here, it's finite. So maybe is it okay? Yeah, maybe we can discuss a bit more about it later. And then as I said, if psi tilde displaces the support of pi tilde, then it's an easy consequence. The spectrum of psi phi is equal to the spectrum of psi. And then you argue by nowhere density and continuity, you show that C of psi phi is equal to C of psi. Okay. And finally, you combine this thing with triangle inequality. I put triangular, sorry, it's triangle inequality, and you get the desired inequality. Okay, it's just algebraic play. And then this is how actually also the main ingredient in the proof of that the capacity of the ball is less than pi r square. The main ingredient is that I'm able to displace the ball by contact isotopy which I can estimate the spectral selector of this contact isotopy, which is if you do. So I'm not very precise here, but if you take the ball and you just translate it like that, as I do on the picture, then you can estimate, and maybe it answers also a little bit the question. If you just take the translation, for example, of this ball, then the capacity, the spectral selectors of your contact isotopy, the energy will be less than 4r squared, where r is the radius of the little ball, which is not good enough because in the theorem I say pi r squared and not 4r squared. And then you have to be a bit more clever about this displacing, and but then you are able to reach this pi r squared. Okay. And so then in the 2 remaining minutes, I just say 2 words about how we show that the capacity of the ball. So we have one inequality. The capacity of the ball is less than pi r squared. So we want the over inequality. And to get the over inequality, actually we start in the contact manifold M1 psi 1. Okay, so in the first prequantization M1 psi 1, it's easy to construct a path of strict contactomorphism supported in the contact ball of radius r, such that we have a very good control on its spectrum. And it's given by t pi r square minus epsilon O0, plus, of course, all the multiple of 2 pi z, since in the first prequantization, the rep flow is 2 pi periodic. It's exactly what the same thing as what happened in symplectic geometry. If you are in a double ball of radius r, it's easy to construct a Hamiltonian function, autonomous, such that let's say the only fixed point of this Hamiltonian function will be the critical point of this Hamiltonian function, and the critical value, you can choose the critical value to be t pi r square minus epsilon and 0. And actually, it's exactly the same construction. You just lift it to prequantization. Okay. So I can go a bit fast here. So, but yeah, the spectrum then will look like that. Okay. And now, since the path of contactomorphism I constructed on the first prequantization was a path of strict contactomorphism, it descends to, you can project it to path on the contact manifold MK psi k. Okay. And then you use the axiomatic property to deduce exactly the proposition. Okay, so you start at time t equals 0. So you have projected your contact isotopy downstairs. So you start at the identity. So C of the identity is 0. But then by non-degeneracy, when t grows, you cannot be on the blue line. You have to go on the red line. And then you go on the red line until you reach this point, which is 2 pi. And then at this point, I don't know if you stay on this red line or you go on the blue line. But at least you will be, it's enough to deduce that the capacity of the ball is bigger than the minimum of pi r squared and 2 pi. Okay, so sorry, maybe I'm a bit over time, but thank you very much for your attention, and I would be glad to receive a question.
Oh, thank you. Any questions?
Yeah, I have a couple of questions. So, in the case of R2N cross S1, so there was kind of extension of original squeezing. Yeah, so that, which says that above Planck kind of constant, you basically cannot squeeze at all.
Yeah.
Can you do the same, or?
Actually, I don't know. I already thought a little bit about it. Actually, received a question, but I didn't. Yeah, I don't know. With the construction I have for the moment, I cannot. I cannot do better. But of course, it is natural to ask, and seems plausible. But yeah, I don't know.
I see. And another question, so from this spectral invariance, I mean, can you produce quasimorphisms or somewhere? Or on contactomorphisms, this would be fantastic, and we know by Borman-Zapolsky that at least in some geometries they exist.
Yeah, actually for the sphere of a complex projective space, so the one that we constructed with Sheila, Sandon, and Simon Allais, from this we can deduce, I think, a quasimorphism. But they are already constructed using a quasimorphism, which is the nonlinear Maslov index. So I don't know also if, but for the other ones, I don't. Actually, I think what is a bit different with the one we constructed with Sheila Sandon and Simon Allais, and the one for strongly orderable prequantization, is that actually I've talked only about one spectral selector here, which is, let's say, the C+. I don't know if you. So there are two maximal ones, the C+, and C-. And for the one constructed with, on the length spaces, C+ minus C- is bounded. So then from this, I think we can deduce that it is a quasimorphism. We can deduce quasimorphism from it. I don't remember exactly.
This would be very interesting to write down.
Yeah, sure. Yeah, but for this strongly orderable prequantization, I don't know if the C+ minus is bounded, the C+ minus C-. That would be very nice. Actually, I also think about it, but I don't know.
Thank you.
Thank you. Yes.
Do you also have squeezing if the two radii are small enough in this framework?
So maybe I repeat the question. So Mihai Damian, which is in this room, asked if the radius are small enough, do we have squeezing? And then I think yes. I think just by applying the same, because I start with this symplectic embedding of the B to N into W, and then when I lift it, I guess it's strictly contactomorphic to B to N times S1, actually. the same as and then I think so. I didn't do it, but yeah, it would be natural also. Just apply the same construction. So for radius small enough, I think we will have squeezing. Yeah, just applying the same result.
So, do you expect that this strongly orderable is a serious? Do you know examples of orderable but not strongly orderable?
Yeah, actually, the conjecture is that it should hold also for orderable, but for the moment, I'm not able to prove it. But and no, I don't know. I don't know example. For example, maybe even I say that there are two theorems: one for the sphere over the complex projective space, and one for strongly orderable. Okay, the sphere is not orderable, but then the real projective space and all length spaces are orderable. So maybe actually it's not two theorems in some sense. And no, I don't have.
If Planck constant is sufficiently small, so your K is sufficiently large, maybe you can prove.
Sorry, can you repeat that?
So again, I mean, we know that sphere is not orderable, right? But projective space is orderable. So what happens physically that you decrease the Planck constant, right?
Yeah.
Yeah. So Planck constant is 1/K. Okay, and so then the kind of intuition could be that when Planck constant is sufficiently small, so then kind of your durability properties are close to perfect.
Yeah. Yeah.
Yeah. So that's what.
Yeah, but I don't know.
Very cautiously, I don't know, of course. Yeah.
Yeah. No, that would be nice to find examples of examples or counter examples of the orderable that are not strongly orderable.
Okay, so if there are no further questions, let's thank Pierre again.